In the previous section, we learned how to differentiate natural logarithms. In this section, we're not necessarily going to be integrating natural logarithms, but we will examine integrals involving the natural logarithm. Now, we've learned that the derivative with respect to x of natural log of x is 1 over x. Essentially, in this section, we will reverse this formula. If the derivative of natural log of x is 1 over x, then we can assume the integral of 1 over x is natural log of x. And that's what the basic rule expresses. The integral of 1 over x dx equals the natural log of the absolute value of x plus c. The only thing you may not have anticipated there is the absolute value bars around the x. That simply ensures that the argument of the logarithm is positive, because we know the domain of a logarithmic function is all positive numbers. Now, we also learned in the last section that the derivative with respect to x of the natural log of a function of x is 1 over that argument times the argument's derivative. So u represents a function of x. So the result of differentiating the natural log of a function of x is a fraction involving a function of x in the denominator times the derivative of a function of x, which is another function of x. So to reverse this formula, we're going to use a u substitution. So the substitution rule, integral of 1 over u du equals the natural log of the absolute value of u plus c, doesn't really look too much different than the first formula. Instead of having an x there, I have a u. But we have to recognize that u is a function of x. So we'll have a function of x in the denominator position. And the derivative of u is another function of x, so we'll have a function of x here as well. Now, we're going to separate this into categories. When we integrate rational functions, we need to identify, are they proper or improper, because we'll handle them both differently. A proper rational function has a numerator of lesser degree than the denominator. So we can make a note here that the degree of the numerator is less than the degree of the denominator. It's a lot like a proper real number fraction. If the number on the top is less than the number on the bottom, we say it's a proper fraction. If we have a proper rational function that we need to integrate, the substitution u equal to the denominator may work. It's something at least we can try. It doesn't always work, and when it doesn't work, we'll look at alternate techniques at that time. So consider example 1, the integral of 5 over 2x plus 7 dx. Observe that we're dealing with a proper rational function. So we're going to take the suggestion and make a u substitution. We're going to say, let u equal the denominator. In that case, du is equal to 2 dx. Notice on the right side, I'm differentiating with respect to x. The derivative of 2x is 2, and the derivative of 7 is 0, so we get 2 dx. So what we want to do is identify the structure of the original integral now in terms of u. One thing that might help on this integral is to take the constant in the numerator and factor it out as a coefficient in front of that integral sign, so that we recognize that we have 1 over u represented as the integrand, and then the leftover in the integrand is the dx. The dx here we can isolate. Notice if we multiply both sides by 1/2, we can see that dx is equal to 1/2 du. So I'm going to rewrite this integral in terms of u, including replacing that dx with 1/2 du. So the integral becomes, let me make some room for my work here, 5 times the integral of 1 over u times 1/2 du. Now that 1/2 we can also factor in front of the integral as a constant, and then you can see the pattern, integral of 1 over u du. If we come back up here to the basic rule, the integral of 1 over u du is the natural log of the absolute value of u plus our arbitrary constant of integration. So this becomes 5/2 times the natural log of the absolute value of u plus c. Now remember, our original integral was in terms of x. So we want our final result also to be in terms of x. So we're going to go back and replace u with its original function in terms of x. So the integral becomes 5/2 times the natural log of the absolute value of 2x plus 7 plus arbitrary constant c. Now remember, because derivatives and integrals are inverse functions, we can check our result by differentiation. If I differentiate the antiderivative, I should arrive at the original function. It's always a good idea to check your work. This will also give us some more practice differentiating logarithms. So we have constant coefficient 5/2. We've learned that to differentiate a natural log, we put the argument in the denominator and the derivative of the argument in the numerator. And of course, the derivative of the constant c is 0. Notice the 2's will cancel and we end up with our original integrand 5 over 2x plus 7. So we can be confident that we got the right answer. Let's try this same technique with a definite integral. We have the integral from e to e squared of x over 10 minus x squared dx. Notice the degree of the numerator is 1, the degree of the denominator is 2, so we are dealing with a proper rational function. In this case, to find the antiderivative, one technique that might work is by letting u equal 10 minus x squared. So when does it not work? Well, when I find du, that is the derivative of the left equal to the derivative of the right, if what I have over here doesn't match the leftovers by a factor, then the substitution technique will not work. Now, let me separate out this integral to be very clear what we're doing. We have 1 over 10 minus x squared. I'm going to write it as times x dx. That way you can see we have right here 1 over 10 minus x squared, that's going to be 1 over u, and the leftovers in the integral are x dx. So we want to make the du statement, we want the leftovers to be isolated over here. So I'm going to isolate the x dx. We can certainly accomplish that by multiplying both sides by negative 1/2. Then we can rewrite our integral in terms of u. We will obtain the integral of 1 over u times negative 1/2 du. Now here's an important thing to observe. We've gone from the variable x to the variable u. The original limits of integration were x values. I cannot use those same limits of integration for an integral in terms of u. So you've got two options here, and I'll show you one option here, maybe the other option on another problem. I'm just going to put stars right there. That reminds me, I cannot plug in e and e squared for u. I can only plug those values in for x. Then I'm going to go ahead and proceed with the integration. Now notice I have a negative 1/2 coefficient. We could move that to the left of the integral, and we've got our familiar formula, integral of 1 over u du. So we have negative 1/2 times the natural log of the absolute value of u. Now this time we don't need the plus c because we're dealing with a definite integral. So this is going to need to be evaluated with the fundamental theorem of calculus. But again, I have stars there to prevent myself from accidentally plugging those in for the variable u. We're going to go back and get our original variable x and plug that in for u, and then we can use those original x values. So I'm going to change colors to show that we're going back to x. We end up with negative 1/2 times the natural log of the absolute value of 10 minus x squared. Now we can evaluate that from e to e squared. So applying the fundamental theorem of calculus, that is, we plug in our upper limit first, and we subtract the antiderivative evaluated at the lower limit. Now notice I'm subtracting a negative, so I'm going to make that a plus, natural log of 10 minus e. Now, we can simplify this a little bit because we have properties of logarithms. So the first thing I'm going to do here is factor out a 1/2. And I want to lead with the positive term. So I'm going to rewrite this as the natural log of 10 minus e minus the natural log of the absolute value of 10 minus e squared. Again, I'm just switching the terms there so that I can lead with the positive. Now, the difference of two logarithms can be condensed into the logarithm of the quotient. The first argument goes in the numerator, and the second argument goes in the denominator. So there we have the exact evaluation of our definite integral. Make sure when you calculate a definite integral that you always give the exact value unless an approximation is requested. Let's go ahead and move on to the next case, that is dealing with an improper rational function. Now remember that for an improper rational function, the degree of the numerator is greater than or equal to the degree of the denominator. A lot like real numbers. So if we have the fraction 4/4, that would be an improper fraction, or 5/4. In the case of 5/4, we could turn it into a mixed fraction if necessary. This is also true for rational functions. If the degree of the numerator is greater than or equal to the denominator, then we're going to do a little bit of algebra to prepare the integrand, and then we'll go back to the technique that we just learned. So to integrate an improper rational function, divide the numerator by the denominator using long division, including the remainder. And then we will integrate the result, also including the remainder. So notice on example 3, the degree of the top is 1, and the degree of the bottom is also 1. This is an improper rational function. So we're going to divide the numerator by the denominator using long division. Now in this case, because you have a linear denominator, you could certainly use synthetic division, but in general, if you have a nonlinear denominator, you'll have to do long division. So I'm just going to take this opportunity to review long division. So I'm going to figure out what can I multiply x by to get 2x. Easily, that is 2. 2 is a constant, so I'm going to put it over here in the constant column. Then I'm going to distribute the 2 to each term of the divisor, 2x plus 2. And then we're going to change the signs just like you do with real number long division. That is, we're going to subtract these terms. So that's going to give us -3. That is our remainder. So we properly express the remainder as a quotient with the divisor. So our integral can be rewritten as the integral of 2 minus 3 over x plus 1 dx. Because we have two terms, we can integrate each term individually. So I'm going to integrate 2 dx. And I'm going to rewrite this as minus 3 times the integral of 1 over x plus 1. Again, I'm just factoring out the constant as a coefficient of the integral. Now, the first term we can integrate directly. The integral of 2 dx is 2x. Now, for this second integral, we're going to have to make a u substitution. Since it is a proper rational function, we're going to use the technique u equal to the denominator. Then du is equal to 1 dx. So we can rewrite this as the integral of 1 over u, and dx becomes du. Copying down our first few terms here, we have 2x minus 3 times the natural log of the absolute value of u, and we do need our arbitrary constant. Now, we'll finish off by recovering the original variable x, replacing u with x plus 1. So we end up with 2x minus 3 times the natural log of the absolute value of x plus 1 plus c. So this is our antiderivative. And as I mentioned before, it's a very good discipline technique to immediately turn around and check your antiderivatives with differentiation to make sure that you've done it right. This not only checks your answer, but it also gives you practice switching from integration to differentiation. So the derivative of 2x is 2, and the derivative of minus 3 natural log of x plus 1 is minus 3 times 1 over x plus 1, where of course the derivative of c is 0. So notice we end up with the proper form of the integrand. 2 minus 3 over x plus 1 matches our original integrand, which was the result of dividing the original using long division. All right, that one's definitely worth practicing again. So let's try our next example. Notice in this example, the degree of the numerator is 2. The degree of the denominator is 1. So this is an improper rational function. Therefore, I have to make it proper by reducing it with long division. Now, notice on this one, our polynomial stops short of the constant term. So I'm going to go ahead and put a placeholder there for the constant term to make the division process go a little easier. Now I'm going to concentrate on this first term and think, what can I multiply x by to get x squared? Well, x times x is x squared. So I'm going to line this up in the x to the power of 1 column, and then we will distribute the x to the divisor. X times x is x squared, and x times 1 is 1x. Then we will subtract and obtain negative 2x, and we can bring down the next term, which is 0. Then we start the process all over again. What can we multiply x by to get negative 2x? Well, that's our constant negative 2, so it's a good thing that we introduce that constant column. Then we're going to distribute. Negative 2 times x is negative 2x. Negative 2 times 1 is negative 2. Now, if your first terms match like they've done on both rounds, then we've done it correctly. Because after we change the signs, those first terms cancel. So it looks like our remainder is 2. Again, to properly express our remainder, we put it over the divisor. So we can rewrite the original integral now as the integral of x minus 2 plus 2 over x plus 1 dx. And then we can integrate term by term. We can start with the integral of x dx minus, I'm going to move the constant to the left, so we have minus 2 times the integral of dx plus 2 times the integral of 1 over x plus 1 dx. So the antiderivative of x, of course, is x squared over 2, or feel free to write that as 1/2 x squared if you prefer, minus 2 times the integral of dx, that gives me minus 2x. Now the last one requires a u substitution, but notice so we recognize here we're dealing with the pattern integral of 1 over u du, which turns out to be the natural log of the absolute value of u, which eventually we would go back and replace with x plus 1. So if you, again, have a coefficient, if you have a linear denominator, you have a coefficient of 1 on your x, then the antiderivative is simply going to be natural log of the absolute value of that denominator. The more you practice, the easier it will get. Now, if you don't see it at this point, write that integral in terms of u and go through the process step by step. All right, let's go ahead and differentiate. So I'm going to find the derivative with respect to x of all that stuff. We're going to end up with 1/2 times 2x minus 2 plus 2 times 1 over x plus 1. So when we simplify, we end up with x minus 2 plus 2 over x plus 1. Notice that matches our simplified integrand, which if we did our long division properly, represents the original. So we can say with confidence that we have the correct antiderivative. Moving on to example 5, notice the degree of the numerator is greater than the degree of the denominator, so this is an improper rational function. Now, because we have a monomial denominator, we do not have to do long division on this one. So you can kind of relax on this one. What you can do with a monomial denominator only is take each term of the numerator and divide them individually by that denominator. And that allows you to skip the process of long division. Just be sure that you understand you can only do that with a monomial denominator, not a polynomial, in this case binomial denominator. That is, I cannot split up a polynomial in a denominator unless I use my long division process. So watch for this case. Monomial denominator makes life a little bit easier. So we can simplify here. Then we can integrate term by term. We can think of that first term as 1/2 times the integral of x dx. And we can think of that last term as minus 3/2 times dx. So integrating, we have 1/2 times x squared over 2 minus 3/2 times x plus c. I'm going to simplify just a bit. And again, you can write this term x squared over 4, or if you prefer, 1/4 x squared. Either is acceptable. So there is our antiderivative. And we will check our derivative. Derivative with respect to x of our result. We get 1/4 times 2x minus 3/2, or x over 2 minus 3/2, which matches our reduced integrand. So we can be confident that we've done it correctly. So at this point, we know that to integrate a proper rational function, we can make the substitution u equal to the denominator, and that may help us find the antiderivative. If we have an improper rational function, we either have to divide it out with long division, or as in the case of example 5, splitting up the numerator over a monomial denominator, reducing, and then integrating. Now, let's look at some miscellaneous fractions. They're going to require a similar substitution, though they're not technically rational functions. Rational functions are the quotient of two polynomial functions. So example 6, we do have a fraction here, but technically it's not a rational function, but we're going to handle it with the same technique. We're going to attempt to let u equal the denominator 1 over cosine of x. Differentiating the left side with respect to u and the right side with respect to x. The derivative of 1 is 0. The derivative of cosine of x is negative sine of x dx. Now, to make this easier to see, I'm going to take one step. You can skip this step if you're with me. I'm going to split up this fraction so you can see where each piece lands. I'm going to write it as the fraction 1 over 1 plus cosine of x times sine of x dx. That way we can see that this part is 1 over u, and the leftovers are sine of x dx, which is very similar to what I have right here. I simply need to divide both sides of this equation by -1. So that's going to give me negative du equals sine of x dx. So I can replace sine of x dx in the original integral with negative du. Now, if these leftovers here, if these leftovers cannot be written in terms of du, then I know that the u substitution, u equal to denominator, does not work. Okay? Now, again, we have the case of a definite integral. 0 and pi over 2 are x values only. So when I rewrite this in terms of u, I cannot plug 0 and pi over 2 in for u. Those can only go in for x. So here's an alternate approach to what we did previously. Instead of using the stars, you can simply update those limits of integration. For example, we can say if x equals 0, then using this equation, u is 1 plus cosine of 0. We know that cosine of 0 is equal to 1, so when x is 0, u is 2. Similarly, if x is equal to my upper limit, pi over 2, then u is 1 plus cosine of pi over 2. Cosine of pi over 2 is 0, so my new upper limit would be 1. So when I rewrite this in terms of u, my lower limit, x equals 0, gets replaced with 2. My upper limit, x equals pi over 2, gets replaced with u equals 1. So I want to be very careful to coordinate the new lower limit with its corresponding lower limit and the new upper limit with its corresponding upper limit. Now, notice the lower limit is bigger than the upper limit. That is a-okay. Again, I've got those correspondences in the right spot. They do not necessarily have to go from a smaller number to a larger number. So now we have the integral from 2 to 1 of 1 over u times negative du. Now let me remind you of a property that you learned from Calculus 1. If you have a negative in your integrand, you can simplify that by reversing the direction of your limits of integration. That is, I'm going to make two changes. The first change, I'm canceling the negative. The second one, I interchange upper and lower limits. Then it looks a little nicer, right? It goes from lower number to higher number. Okay, the antiderivative of 1 over u is the natural log of the absolute value of u. In a definite integral setting, we do not need the plus c, and we don't have to go back and recover the original variable because remember, we updated our x values to u values. So we can go ahead and plug in our numbers. Remember, the natural log of 1 is equal to 0. So we end up with the natural log of the absolute value of 2. Now, this may seem a little bit picky, but natural log of the absolute value of 2 stands to be simplified. 2 is positive, so the absolute value bars are redundant, so I'm going to simplify it by dropping those absolute value bars. So the result of our definite integral here is natural log of 2. So even though this wasn't a rational function, we used the same technique, u equal to the denominator, and we ended up with an antiderivative involving a natural log function. Let's consider the next definite integral. We have the integral from 1 to e of the natural log of x divided by x dx. Now, if I recognize this is a fraction and I continue with the same thing I've been doing, that is u equal to the denominator, I end up with du equals dx. So when I go to rewrite this in terms of u, I cannot write the leftovers, natural log of x, in terms of u. So this substitution will not work because I cannot convert every factor in that integrand to a function of u. So let's try something different on this one. Let's let u equal the numerator on this one. Well, if u is equal to the numerator, then du is 1 over x dx. Now, this is going to work beautifully. Again, I'm going to split up this fraction. I'm going to call it natural log of x times 1 over x dx. If you see it, you don't have to do that. This is just for explanation purposes. Because then we can observe natural log of x will be replaced by u, and 1 over x dx we've got right here as du. Now again, I'm going to show you the option of updating your limits of integration. We could say when, now remember these are x values, when x equals 1, here's the relationship between u and x. When x equals 1, then u equals natural log of 1 or 0. And my other x value, when x equals e, u equals natural log of e, and natural log of e equals 1. So when I convert my integral to u values, I also update my limits of integration. So when x is equal to 1, u is equal to 0. When x is equal to e, u is equal to 1. So we have a very simple integral to calculate u du. The antiderivative there, of course, is u squared over 2, and we can evaluate directly. Plugging in our upper limit minus our lower limit, we end up with 1/2 for the value of our definite integral. So in that case, u equal to the numerator was the substitution that worked. You want to train yourself to recognize that 1 over x as, or the dx over x, as the derivative of the natural log. When you recognize that pattern, you're seeing the overall structure of the integral, which is how you find the antiderivative. Notice example 8 is really similar. Instead of natural log of x over x, we have natural log squared of x. But we can use the same substitution, because if u is natural log of x, and again, du is 1 over x dx, then we can see that this integral, natural log squared of x times 1 over x dx, is really only different by an exponent. That natural log squared will be u squared. The 1 over x dx is du. So in terms of u, we have the integral of u squared du, which becomes, by the power rule, either u cubed over 3, or if you prefer, 1/3 u cubed. And in the indefinite integral situation, we do need our constant of integration. Now, the original integral was in terms of x, so we want to make sure we end up with an integral in terms of x. So u was natural log of x. I'm replacing u with natural log of x, but we're going to have to cube it and then add c. Let's definitely check this one by differentiation since it's an indefinite integral. This will give us some great practice with derivatives of logarithms. So we have 1/3 times the derivative of natural log cubed of x. So we're going to start with our power rule. That is, the power comes down in front. We decrease the power by 1, keeping the base the same, and then we multiply by the derivative of the base. So when we cancel our 3's, we end up with natural log squared of x over x, which was our original integrand. So our answer is definitely correct. All right, we're going to end this section on kind of a tricky example here. We have the integral of 1 over 1 plus the square root of 2x dx. So we're going to start with the suggested substitution, u equal the denominator. Now, you may want to recognize that square root there is 2x to the 1/2 power. So when I find du, of course the derivative of 1 is 0, we're going to have to apply the chain rule. So we have the power 1/2 down in front, the base stays the same, we subtract 1 from the exponent, and then we multiply by the derivative of the base. Notice the 2's here cancel, and we can rewrite that 2x to the negative 1/2 as 1 over 2x to the 1/2, or maybe it would be easier to see it 1 over the square root of 2x. Oh, and I lost my dx. Don't lose your dx like I did. Okay, got it back. So looking at our original integral then, we have the integral of, remember this is u, 1 over u. Now we need to replace dx with a function of u. But if I solve for dx in this case, I'm going to have a function of x times du. And we don't ever want to have mismatched variables like that. So I cannot have an integrand that has both an x and a u at the same time. It can either be in terms of x or u, not both. But if I go back up here to my original substitution, notice if you subtract 1 from both sides, you can rewrite that square root of 2x in terms of u. So the square root of 2x can get replaced by u minus 1 du, and then I can rewrite this dx in terms of u. Okay, I'm switching variables here. Let me switch colors just to catch your attention. So this is 1 over u times dx, which is u minus 1 du. So it is a little simpler. There's no radical there, but now I got to figure out how do I integrate this. Now, if I go ahead and multiply that fraction by u minus 1, you may recognize what to do. Observe here that we have an improper rational function. That is, the degree of the top is equal to the degree of the bottom. So we can reduce the rational function and then integrate. Further, notice that we have a monomial denominator. That makes it very convenient to reduce. We're simply going to divide both terms of the numerator by that monomial denominator and simplify. Now we can integrate term by term. The integral of 1 with respect to u is u, and the integral of 1 over u is the natural log of the absolute value of u. And since it is an indefinite integral, we will add our constant of integration. Now let's go back and recover our original variable. Remember, u is 1 plus the square root of 2x. So we're going to replace that first u with 1 plus the square root of 2x, and we're going to replace that second u also with the same thing. And we've got our arbitrary constant. So we have our antiderivative in terms of x. So this particular case is rare. In general, you want to avoid this situation where you've got mixed variables, but because of our original substitution, we were able to rewrite dx completely in terms of du. So when integrating proper and improper rational functions, generally we let u equal the denominator, and that also works for some miscellaneous fractions. All right, this is a lot of technique to practice. The more you practice, the easier it will get, the more you will be able to see those overall patterns. So best of luck on the homework. Let me know when you have questions.